So, we were discussing about the higher order differential equations, boundary value problems of more than 2 order. So, in that case it leads to a system of block tridiagonal matrix. So, that means we get a system in which every entry of the matrix is a submatrix, square matrix. So, basically what we found is that Ax equal to let us call D, where x, the component of x itself is have some vectors. So, x1, x2, xn, say, which are each of xi are say 1 cross m vectors, and the matrix A is something like say B1 C1 0 0 0 A2 B2 C2 0. So, remaining all are 0. So, you can put a 0 over here, and the last one, say let us call this is A N B N. So, this is the situation. So, where each of these AI, BI, CI are say let us call M cross M matrices, and the known vector, the vector D is say let us call this is the form D1, D2, Dn. So, or these are the vectors. So, these are also these each of Di are 1 cross M vectors. So, what we need is to solve this for x, where that x satisfy this block tridiagonal system. So, the similar procedure as adopted in Thomas algorithm. So, that means reducing it to a triangular form, these matrices, the tridiagonal block tridiagonal form by block elimination. So, what we need to do is that we will bring 0 at these AI positions. So, AI should be transferred to a null matrix, and BI should be transferred to a identity matrix, and obviously CI will not keep quiet, it will transfer to some other CI dash. So, the resulting situation will be a form like this: 1 C1 dash 0 1 C2 dash 0 0 0, all are 0 over here, and the last but one is say 1 C n minus 1 dash, and this is 1. So, this is the situation into x1, x2, xn. This is equal to the transformed vector, which we call as d1 dash, d2 dash, dn dash. So, once I get a system like this, then the solution is very easy. Solution we can write as from here xn equal to the dn dash, and generally xi equal to di dash minus ci plus ci dash di, sorry, this is xi plus 1. So, this is xi plus 1, this is the vector xi plus 1, where I equal to n minus 1, n minus 2, 2, 2, 1, etc. So, by back substitution one can obtain the solution. So, this last one, like the Thomas algorithm. So, the last one we first get, and then subsequently all this all the vectors of unknown. So, each of xi are vector 1 cross m. Now, so what is remaining is how to get this di dash and ci dash. So, the algorithm gives us the way of finding these di dash and bi dash. So, this di dash and ci dash are obtained as follows. as follows. So, first one can obtain the C1 dash, which is quite evident, B1 inverse C1 and D1 dash equal to B1 inverse D1. So, this is the two elements for I equal to 2 to n minus n here. So, this is Bi dash, this is a in between matrix which we do not require to store once we get these other coefficients. Ci dash is equal to Bi dash inverse Ci and Di dash equal to Bi dash inverse Di minus Ai d dash I minus 1. So, this is for I equal to 1 to n. So, once we complete this, we get the whole coefficients, reduced coefficients or reduced form of the block tridiagonal matrix. So, this gives us the complete algorithm. So, that means what we need to do is we fit the coefficients of discretized equation, the corresponding coefficients as Bi, Ci, etc., Ai, Bi, Ci, etc. From there, we construct the Ai dash and Di dash and so on. So, one can obtain the block tridiagonal. So, construct the block tridiagonal matrix to solve the following PBP. One say y triple dash plus 4y double dash plus y dash minus 6y equal to 1, y 0 equal to y dash 0 equal to 0 and y dash 1 equal to 1. Say the question 2, we can have fourth order 81y equal to 81x square, and you have given the condition y 0 equal to y 1 equal to y double dash 0 equal to y double dash 1 equal to 0. Now, in many cases, as we have started with, that we can directly solve by this fourth order or third order. We can reduce to a we can use 5-point formula and get a system of equations, but the thing is that we won't get a tridiagonal form, because there will be 5 unknown variable, 5 grids are involved at each location. At each xi grid points is associated with I minus 2 to I plus 2. So, which rules out the consideration of tridiagonal system. Now, if you do not have a tridiagonal, the thing is we won't get a direct method to solve this. But if I go by this manner, say let p equal to y double dash and p double dash becomes 81y equal to 81x square. So, this is a system of 2 second order equation with boundary conditions are y 0 equal to p 0 equal to 0 and y 1 equal to p 1 equal to 0. So, any number of grid points, one can obtain a block structure corresponding to this and can apply the block tridiagonal algorithm what we just described and get the solution for any choice of the grid points. So, this is about the linear situation. Now, when we have a nonlinear situation, so things become quite complicated, because if we have a nonlinear differential equations, now if we apply the finite difference scheme, central difference or whatever scheme. So, it will lead to a system of nonlinear equation. So, it is expected, say we now go for nonlinear BBP. So, to solve this nonlinear BBP, so nonlinear BBP means it will be of any form x, y, y dash, y is a equal to say y a, and y b, y at b is y b. So, we need to solve this for a less than x less than b. So, if I discretized equation looks like will be of this form. Equations are, if I at the discretized equation, say at grid point I will be f I y I minus 1 y I plus 1 equal to 0. This kind of equations we can get for I equal to 1 to n minus 1. To our notations, whatever notations we have used, we have taken the grids as xi, and we need to find out the yi from I equal to 1 to n minus 1. So, if I discretize at each grid point, we use the central difference scheme for y double dash, y dash. So, we get a. Now, if f is a nonlinear function of y, y dash and y dash, then f I will also become nonlinear, becomes nonlinear combination, also becomes nonlinear with respect to yi minus 1, yi plus 1, etc. So, now that algebraic equation, whatever the will also become, where f I is a, needless to say that f I is an algebraic equation which are involving yi's in a nonlinear fashion. Now, reducing it to a matrix form is ruled out, is not going to be possible for this nonlinear set of equations. So, if we have grids say n, so now we get n minus 1 number of grid points, and for each you have a equation as given by this way. Now, to do that, we use the Newton-Raphson method to cope with the nonlinearity. So, we solve this equation by Newton's linearization technique. So, it is an iterative procedure. Now, before I talk about the Newton's linearization technique with respect to the nonlinear boundary value problem, so first recall what is that Newton-Raphson method for finding root. Now, Newton-Raphson method to find a root, what do we do to find a root of say f x equal to 0 and algebraic equation, some equation accidental or algebraic or whatever. So, what we do is let alpha be the root which we determine iteratively at k plus kth iteration, alpha k be the approximation of alpha So, we can write alpha equal to alpha k plus some error, because obviously this is not the same as the root k. So, let us put here as k as superscript, because so that we can distinguish it with the iteration index, where k is k greater than or equal to 0 is the iteration index. So, let us call this error as so alpha equal to alpha k plus delta alpha is the error. So, obviously, so f of alpha k plus delta alpha equal to 0, because it is the exact solution of the root. Now, if we expand by Taylor series, so what I get is 0 equal to f alpha k plus delta alpha into df, because here it is only single variable. So, dx, this is approximation value k, that means x is replaced by alpha k, then delta alpha whole square by 2 factorial d2f dx 2 k, k means alpha equal to alpha k plus etc. Okay. Now, where what we notation denotes that this is ddx of fx at x equal to alpha k. This is the notation we have used. Similarly, the second order and all. Now, what we find that this is a which is a power series of delta alpha. So, all this with superscript k, variables with superscript k are known. So, basically this is an equation for delta alpha. So, if you solve the infinite degree polynomial and get delta alpha, you get the exact solution, which is not possible. So, what I do is we can solve very easily up to the linear order terms. So, we retain up to the linear order and drop all these terms beyond this. So, if we do that, so what I get a approximation. So, retaining only up to linear order, of delta alpha, we get f alpha k plus delta alpha f dash alpha k. This is also we can write in this way equal to 0. So, this gives you delta alpha, which is the error at the kth iteration, as f alpha k by f dash alpha k. So, obviously, this error is not the exactly the same as the error we are looking for. So, we call the next approximation for alpha as alpha k plus 1 equal to alpha k minus f alpha k by f dash alpha k. So, basically what we are doing is k greater than or equal to 0. Basically what we are doing is we are getting an approximate value of the error at the kth iteration by this manner, and then we are adding to the existing value alpha k to get the modified value alpha k plus 1. So, this is the way subsequent iteration proceeds. So, for convergence of this iteration, we need that delta alpha k. So, what I need is for convergence that two successive iterated values should be very small, where epsilon is a say something like 0.5 into 10 to the power minus 5 and show very small quantity. So, or in other words, if we get delta alpha is less than epsilon, so iteration converge. So, this is how the Newton-Raphson method for finding a root of a nonlinear equation is done. The same procedure will adopt here for the case of a nonlinear boundary value problem. So, the nonlinear boundary value problem, what we do is we go back to our nonlinear cases, nonlinear VVB. So, we have a phi at any grid point xi. The discretized equation is phi yi minus 1 yi plus 1 equal to 0. Now, we substitute, we solve this equation. This is for I equal to 1 to n minus 1. So, we solve this set of n minus 1 nonlinear, here it is algebraic equations iteratively through the Newton's linearization technique. For that, what we do at any iteration, let yik be the approximate value, of yi, and we can write this yi equal to yik plus some error delta yi, where delta yi is the error of approximation. At this kth iteration, I equal to 1, 2, etc. n minus 1. At the two ends, I equal to 0 and n, we have given the yi, so we need not have to find out the value of yi, so we can take delta yi is 0. So, if I substitute, so we must have this yik plus delta yi minus 1, this is delta yi minus 1 plus yik plus delta yi plus yi plus 1 k plus delta yi plus 1. So, basically what we need is, we need to find out these errors. So, to do that, we expand by Taylor series as we did for Newton-Raphson method. So, what we get is here phi yi minus 1 k, yi k, yi plus 1 k plus delta. There are three variables here, yi minus 1. So, we take a partial derivative delta yi minus 1. This is that all the variables are evaluated at kth iteration. So, this is known, this coefficient is known. So this is delta fi by delta yi k plus delta yi plus 1 into del fi by del yi plus 1 k plus all the higher orders. So this is equal to 0. So here all with superscript, one thing need to be known, variables with superscript k are known. So if we now retain only up to the linear orders of delta yi's, so what I get is retaining only up to linear order orders of delta yi's, we get fi. So we get a equation which is linear in delta fi delta yi minus 1 k plus delta yi delta fi delta yi k plus delta yi plus 1 delta fi by delta yi plus 1 k equal to, this is known, so I transfer to the other side. So fi yi minus 1 k yi k yi plus 1 k. So this is for I equal to 1 to n minus 1. So that means with delta y 0 equal to delta y n equal to 0, because we are not doing any iteration at the two boundary points where values are given. So which forms a n minus 1 number of linear, these are linear algebraic equations involving n minus 1 unknowns delta y1, delta y2 up to delta yn minus 1. This is said yields a tridiagonal system. One can very easily see that this forms a tridiagonal system, Ax equal to b, where x transpose is this vector delta y1, delta y2, delta yn minus 1. So solution of which will give you the x. So once I obtain the solution, the successive approximation for yi's are obtained as yi k plus 1, this is our next approximated value, this was the old one, plus whatever the value we obtain now for I equal to 1 to n minus 1. So this is the iteration procedure as to we proceed like this way. So that means every iteration we are basically solving a tridiagonal system given by this Ax equal to b. Once I solve, I get the error vector delta y1, delta y2, delta yn minus 1 at the kth iteration, and k is greater than equal to 0. So once I get this delta yi's, I add it to the previous iterated value yik and get the updated value yik plus 1. So iteration procedure should go on till we get iteration procedure converges when max of 1 less than equal to I less than equal to n, delta yi is less than epsilon. It is as good as saying the two successive iterated values are less than epsilon. So, in that situation epsilon is a pre-assigned small positive number. Now, here we can see that to start the iteration, a guess for yi's, that is yi 0 for I equal to 1, 2 up to n minus 1 need to be supplied, provided or assumed. Now, this method does not give any clue to how to choose these yi zeros, but one attractive feature is that the quadratic rate of convergence. A rate of convergence occurs for this technique. That means if we get a convergence, it converges very fast within few steps itself. So, this is a very biggest advantage to solve the nonlinear equation. So, basically what we do in the Newton-Raphson Newton's linearization procedure is that we have the nonlinear boundary value problem, which we discretized through the scheme whatever we fill, say central difference scheme, and that will lead to a set of nonlinear algebraic equation of the grid point values. So, at each grid we assume some value as yi 0, and then subsequent values are obtained by choosing a error yi and plus yi k plus 1 we take as yi k plus delta yi. That delta I satisfy a linear system which forms a tridiagonal. So, one can solve this with y 0 as 0.5 and y pi is minus 0.5. So, this is a nonlinear. Now, one thing to be remembered that here whenever we talk about the nonlinearities, we talk about the nonlinearities of y's, not about the x. So, another third order equation, this is very common equation which appears in fluid dynamics, boundary layer flow past a wedge. So, this is 0, f dash 0 is 0 and f dash 10 equal to 1. So, solving this set of equations is require the computer programming, but one can get a tridiagonal system. So, for this case it is to be block tridiagonal, because if I substitute f equal to f dash, so we get f double dash plus f dash plus 1 minus f square equal to 0. So, it is a nonlinear system with condition as f 0 equal to f 0 equal to 0 and f 10 equal to 1. So, this kind of system using the Newton's linearization technique, one can derive the block tridiagonal form, and the iteration procedure will provide the approximate solution at every iteration. Okay, now one more problem I can give is, this is the 3y y double dash plus y dash whole square equal to 0, y0 equal to 0, y1 equal to 1. Then another is, this is for the Hamel flow through an orifice. There is a orifice fluid dynamics problem, orifice flow past orifice. If you have a small orifice, f double dash is the flux, which is given as k, and f dash omega is 0, k is taken to be 0.1 here, and omega is 0.87. So next we will talk about the partial differential equation, that is functions of which is depending on more than one variable, in the next lecture. Thank you.